Hi everyone. In this video, we're going to be looking at the graphs of sine and cosine. So you might remember a few videos back, I told you that one of the main goals of this class was to get comfortable with trigonometric functions so that we could add them to the list of functions that you know, along with linear functions, polynomials, rational functions, exponential functions. We want to be able to add trigonometric functions to that list. And so first, we really need to focus on how do you actually evaluate trigonometric functions? And that has been the focus of the last few videos, right? Is, how do you do something like evaluating sine of negative pi over 2 or cosine of 7 pi over 3? But now that we've developed that comfort with actually evaluating the trig functions, now we're ready to kind of do a little bit more with these functions. So like I said, in this video, the focus is going to be on looking at sine and cosine as functions and looking at what their graphs look like, and then also trying to understand why their graphs look the way they do. So the first thing that is going to be a little bit new in this video that we have to get accustomed to is actually using function notation with trigonometric functions. So you've heard me refer to them as trigonometric functions, but we haven't been using function notation, right? Like for example, we were just kind of evaluating things that looked like this, like cosine of pi over 6, just kind of on its own without any function name associated with it. And so what we're going to be doing first in this video is just practicing a little bit with looking at sine and cosine as functions with function notation. So in this video, I'm going to use f to be the function that goes with sine. I'm going to use g as a function that goes with cosine. There's nothing special about that. That's just the letters I'm choosing to use in this video. Another thing you might notice is that the input variable that's being used here is t. That's what your book uses. You could use a different variable. So if you like theta better, you could call this function instead f of theta is equal to sine of theta. If you like x better, you can call it f of x is equal to sine of x. If you like, I don't know, w better, you can call it f of w is equal to sine of w. My point is that the variable doesn't matter, right? As long as the variable on, within your left-hand side matches the variable on your right-hand side, the meaning is the same no matter which variable you choose. The reason that I think we're using t is that it's a little less clunky than theta, but it's kind of similar to theta, right? You can think of it as standing for theta. So yeah, that's a variable we'll be using here. Okay, so how do these functions work? Well, like with any other function, the variable that you see in the parentheses is your input variable. So we're going to be using t to represent our input. And so what kind of things are getting input into trigonometric functions? Well, angles, right? So the input of a trigonometric function is always going to be an angle. So in this case, we're using t to represent whatever that angle is. And so I'm going to put the same thing under cosine. So input is an angle. And so then what would the output be? Well, it would be sine or cosine of the angle, right? So for example, for f of t is equal to sine of t, you plug in an angle t, and what comes out as your output? Well, sine of that angle. And we'll do an example in a second. We've seen that we use the unit circle to actually calculate sine and cosine of an input, of an angle. But really the input's an angle, the output is just sine of that angle, and then for cosine, the output is cosine of that angle. Okay, so let's do a quick example. So for example, let's say that, still using f of t representing sine of t and g of t representing cosine of t, we want to evaluate f and g of 2 pi over 3. So for example, for evaluating f of 2 pi over 3, we would just say, okay, well, we know that the function f of t is supposed to be sine of t. So f of 2 pi over 3 is going to be sine of 2 pi over 3. So it just works like any other function, right? With any function, you take your input and you just replace the input variable with whatever that input is, and that's what we're doing here. Then there is kind of one more step though, right? It's not immediately obvious what sine of 2 pi over 3 is. We have to actually calculate it, and that's where the unit circle comes in. So 2 pi over 3, we know that that is 2 times pi over 3. So that's 2 times 60 degrees. So that's going to put us over here, 120 degrees. And then if you were to draw a right triangle, it would be a 30, 60, 90 triangle. And then the shorter side is the x coordinate, right? So the shorter side is going to be negative 1/2 in this case, because the length is 1/2, but we're in quadrant 2. And then the longer side is going to be our y coordinate, and that's going to be positive. And so it's positive square root of 3 over 2. So we've learned that to find sine of an angle, you take the y coordinate of the terminal point. And so sine of 2 pi over 3 is going to be square root of 3 over 2, because that is our y coordinate. And then, and actually let me just rewrite this just to make it really clear. So what we just found is that f of 2 pi over 3 is equal to square root of 3 over 2. So just like with any other kind of function, we take our input, we plug it in, we figure out what that number is, and that is our output. So similarly, if we wanted to find g of 2 pi over 3, so in this video, we're using the function g of t is equal to cosine of t. And so g of 2 pi over 3 is the same thing as cosine of 2 pi over 3. So just plugging in 2 pi over 3 for t. And then we know that cosine corresponds to the x coordinate of our terminal point. And so in this case, we saw that x coordinate is negative 1/2. And so we can conclude that g of 2 pi over 3 is equal to negative 1/2. So that's all that's going on with function notation. It's just kind of like one extra layer. Okay, so now I want to talk about what is the relationship between a function and its graph, right? Because the goal of this video is to sketch the graphs of these two functions, f of t is equal to sine of t and g of t is equal to cosine of t. So in order to answer that question, I actually want to look at a much simpler example of a function just to kind of remind you in general, what is the relationship between a function and its graph? So as I just said, in general, what is the relationship between a function and its graph? So if you have the graph of a function and you look at all of the points that lie on that graph, those points are going to be, they're going to have a horizontal coordinate, which is the input, and a vertical coordinate, which is the output, right? So let me kind of write that down here. So points on the graph will be of the form input, comma, output. And by the way, you'll hear me say like horizontal coordinate instead of x coordinate, and that's just because for the functions we're working with in this video, because we're using an input variable of t, I don't want to say x coordinate, but t coordinate maybe is a little confusing. So I'm just going to say horizontal coordinate when I'm talking about the horizontal coordinate. So points on the graph of any function will be of the form input, comma, output. So basically, in other words, this means that the horizontal coordinates are the inputs, while the vertical coordinates, so that's what you might think of as the y coordinates, are the outputs. So again, what I just wrote down is true for any function. So I just want to look at a very simple example just to kind of, when we get to sine and cosine, we'll see there's just like another layer of complication. So I think if you end up getting it all confused with that, going back to a very simple example might help you make sense of how the graphs of sine and cosine work. Okay, so let's say, for example, we wanted to sketch the graph of f of t is equal to t squared plus 1. So you might be familiar enough with what this graph looks like to sketch it without drawing or without making a table, right? Because it's just a basic parabola that's been shifted up by 1. But let's say you didn't remember that. How would you actually go about graphing it? Well, you could just plug in a bunch of points for t and see what you get as your outputs. So for example, if you plug in -2 for t, you would get -2 squared plus 1, so that gives you 5. If you plug in -1, -1 squared plus 1 gives you 2. If you plug in 0, 0 squared plus 1 gives you 1. Plug in 1, 1 squared plus 1 gives you 2. Plug in 2, 2 squared plus 1 gives you 5. And so then how would you kind of turn this table into your graph? Well, basically, you would interpret each of your inputs as an x-coordinate and then the corresponding output as the y-coordinate, or I should say horizontal and vertical coordinate. So for example, we would have the point -2, 5. We would have the point -1, 2. We'd have the point 0, 1. We'd have the point 1, 2, and we'd have the point 2, 5. And then from there, you can kind of just fill in the space between, because you have some familiarity with what the shape of this graph looks like, right? We know it's a parabola, and so we kind of can fill in the space between and say that our graph looks like this. Okay, so it's going to be the exact same idea when we get to the graphs of sine and cosine. So before we get to actually sketching those graphs, I want to kind of do one more thing with what we did above. So in each of these statements that we wrote down, we found that f of 2 pi over 3 is square root of 3 over 2, and that g of 2 pi over 3 is -1/2. I want you to think for a moment about, what did these two statements that I'm circling in orange, what do those tell you about points that lie on the graphs of f of t is equal to sine of t and g of t is equal to cosine of t? Like, from what we wrote down for each of these, can you identify one point that lies on the graph of f of t is equal to sine of t and one point that lies on the graph of g of t is equal to cosine of t? So basically, it's the same idea as what we were doing below, right? We have our input here, and we have our output here. And so we know that points that lie on the graph of f of t is equal to sine of t are going to have the form input comma output. And so this tells us that the point 2 pi over 3 comma square root of 3 over 2 lies on the graph of f of t is equal to sine of t. Right? Because that's just how functions work. You find the input and the output, that's your point. And so when we go and actually graph these functions, we'll see that our inputs, our horizontal axis is going to consist of all the angles, and then our outputs, the vertical axis, is going to consist of all of the sines and cosines of those angles. And so similarly over here, what we can say is that we now know that the point 2 pi over 3 -1/2, well, that point must be a point that lies on the graph of g of t is equal to cosine of t. So one point that kind of seems to get some students a little bit confused is, well, what about this point? What's the deal? How does that fit into everything? Isn't that a point that's on the graphs of sine and cosine? Well, no, it's not. That is a point that lies on the unit circle. And one thing I just want to make really clear in this video is that the unit circle is not the same as the graphs of sine and cosine. So what is the unit circle? The unit circle is just a circle with a radius of 1. It has its own equation, right? The equation of the unit circle is x squared plus y squared is equal to 1. The unit circle is a tool that we can use to evaluate sine and cosine, but it is not the graph of sine or cosine, because we know that the way that the graphs of sine and cosine should work is that we should have angles as our inputs and sines and cosines of those angles as our outputs. And so that just doesn't really match up with the unit circle. So make sure you're not kind of mixing them up in your head. Unit circle is its whole own separate thing. It's a tool for evaluating trig functions, but it is not itself a graph of a trigonometric function. Okay, so let's start actually doing what we need to do to sketch the graphs of these functions. So again, we're going to be trying to graph f of t is equal to sine of t, and then g of t is equal to cosine of t. And so we're going to do this the same way that we just did the previous example, right, where we just made a brief table. The only difference is that, so when we were doing this example, it was very easy to calculate the outputs, right? The outputs we could just do by like doing the number squared plus 1. You could kind of even do it in your head. Compared to for sine and cosine, finding the outputs is not going to be as easy. We have to actually use the unit circle, right, to calculate what sine and cosine of these different numbers are. But other than that, it's exactly the same process. We're just making a table where we list out our inputs and we find our outputs, and then we graph each of those pairs of inputs and outputs as a point on our graph. Okay, so let's start by we're going to kind of do both sine and cosine at once because they're using the same angles. Let's start with an input of 0. So let's say we wanted to evaluate f of 0. So f of 0 would be sine of 0. And so to evaluate sine of 0, that means going to an angle of 0 on the unit circle and finding the coordinates of the terminal point at 0. And so the coordinates of this point are 1, 0. And so we know that sine is equal to the y coordinate on the unit circle. And so that tells us that f of 0 is equal to 0. On the other hand, for cosine, so if we want to evaluate g of 0, we know that that corresponds to the x coordinate on the unit circle. And so g of 0 would mean cosine of 0, and that is equal to 1. So we've already now established a point that must lie on the graph of sine and a point that must lie on the graph of cosine. Okay, so next up we have pi over 6. So pi over 6 we know is like a 30-degree angle. And I'm not going to draw all the right triangles. If you're still a little shaky on how these coordinates of the terminal point are found, I would recommend going back to some of the previous videos where we really went through that. If I did that for all of these angles, it would just make this video way too long. So I'm just going to kind of jump to writing down what the terminal point is, but I don't want you to think that you should like have it memorized or something. It's fine if you do it by drawing the triangle. I actually recommend that you do it by drawing the triangle. I'm just not going to do all of that in this video for the sake of time. So when your angle is pi over 6, you should be able to find that the coordinates of the terminal point are square root of 3 over 2 as the x coordinate and 1/2 as the y coordinate. And so that tells us that f of pi over 6, which in this case represents sine of pi over 6, that is the y coordinate on the unit circle, and so that is equal to 1/2. Whereas g of pi over 6, that would mean cosine of pi over 6, that is equal to square root of 3 over 2, the x coordinate from the unit circle. And so we have two more points to add to our table. So we have 1/2 for f of pi over 6, and we have square root of 3 over 2 for g of pi over 6. Because we're going to be graphing these points, we need to know approximately the value of square root of 3 over 2. So if we type it into a calculator, you'll find that it's equal to about 0.87. So that's just going to help us when we go and actually plot these points in a few minutes. That will help us figure out exactly where to put that y coordinate. Okay, pi over 4. And I would recommend, by the way, that you pause the video and try just filling out the rest of these yourself. So you might notice I filled out a lot of this table. We're just going to do up through pi over 2 together, and then we'll just have the rest of them already filled out, because otherwise this video would be very long. But yeah, I encourage you to pause and try to fill out just this kind of top portion of the table. Okay, so pi over 4, we know that that is a 45-degree angle, and so we know the coordinates of that point are square root of 2 over 2 and square root of 2 over 2. And so that means that both sine and cosine are equal to square root of 2 over 2. So g of pi over 4 is equal to square root of 2 over 2, and same thing with f of pi over 4. And so for those ones as well, we want to type that into a calculator to get an idea of where that's going to fall. And so it's approximately equal to 0.71. Okay, pi over 3. So that is a 60-degree angle. And so the coordinates of that point are going to be 1/2 square root of 3 over 2. Again, okay, if you don't know that off the top of your head, you can always draw a right triangle. And so f of pi over 3 would be sine of pi over 3. And so we're looking at the y coordinate, and we get square root of 3 over 2. And so we can put that into our table. We know that that's approximately equal to 0.87. And then g of pi over 3, so cosine of pi over 3, that would be equal to 1/2. Okay, last one that we're doing together is pi over 2. So pi over 2 is a 90-degree angle. And so the coordinates of that point are 0, 1. And so that tells us that f of pi over 2, so sine of pi over 2, is equal to 1, whereas g of pi over 2, which is cosine of pi over 2, that is equal to 0. So we can put 1 and we can put 0. Okay, so we're going to focus now on looking at the graph of f of t is equal to sine of t. So you can kind of like forget about the table on the right-hand side, focus on the table on the left-hand side. And like I said, I'll just write this down for your notes. All of this stuff, this is also calculated using the unit circle. So again, I'm not going through it. You're welcome to do it yourself and confirm that these are correct. But if you did want to calculate all of these, you would just do the same process we just did for the first few. So you just keep evaluating sine and cosine of all these different angles. And I'll get to this later, but notice that I included basically all of the kind of nice angles between 0 and 2 pi. Those are not the only angles that you can plug in, but it's kind of like when we did our table here. We didn't do like every value of t, right? We just picked a few, kind of like that. We're just picking some nice values, and then we'll talk about what the rest of the graph looks like as well. Okay, so let's start again by focusing on the table on the left. So I'm going to start by just plotting a few of the points that we came up with. So the first point that we came up with here is 0, 0, right? So we want to plot that as a point. As I mentioned before, notice that the horizontal axis is labeled in terms of pi. So this might be really tiny on your screen, so I apologize for that, but in the lecture notes, it should be a little more legible. And you might notice I had to add in the multiples of pi over 4 because they weren't on the grid that I used here. So our first point that we're going to plot is the point 0, 0. So I'm just going to plot 0, 0. Okay, so our next point is the point pi over 6, 1/2. So I'm going to choose pi over 6 as my horizontal coordinate and 1/2 as my vertical coordinate. So here's pi over 6 as the input, and then 1/2 as the output would be up here. Okay, next we have the point pi over 4, and then square root of 2 over 2, which we know now is about 0.71. So pi over 4, I had to write that in myself, but that's here. And then 0.71 should be somewhere just a little bit below 0.75. So maybe somewhere like that. Okay, next up we have pi over 3. So pi over 3, we know that when pi over 3 is the input, the output should be about 0.87. So 0.87, let's see, that's going to be somewhere between 0.75 and 1, a little bit closer to 1, maybe somewhere like that, maybe a little lower actually. And then the last point that we did together was when the input is pi over 2, we saw that the output was 1. So that's going to be this point here. So those are all the points that we came up with together. I'm now just going to go and plot the rest of these points. So I'm going to do it rather quickly, but just trust that it's the same as what we did before, right? I'm just taking inputs and outputs and just kind of putting them down. Okay, so it would look something like this if you went and plotted all the rest of the points on the table. And so now I'm going to fill in between those points because we know that these are not the only values that you can take sine of, right? You can take sine of any angle. And for example, you could do an angle that's between 0 and pi over 6. And so it's going to fill in basically smoothly between all of those points. So this is what the graph looks like. It's this kind of curved shape. And I'll talk more about this in a minute when we're done graphing cosine. But you can see that it kind of starts at 0. So it has its y-intercept at 0. It goes up to a maximum height of 1. It goes back down to 0, goes down to -1, and comes back up to its final height of 0. Okay, so let's do the same thing for cosine. So I'm going to start by plotting the points that we have up here. So in this case, we have the point 0, 1. And then when the input is pi over 6, the output is 0.87. So pi over 6 and 0.87. When the input is pi over 4, the output is about 0.71. When the input is pi over 3, the output is 1/2. And when the input is pi over 2, the output is 0. And then similarly, I'm just going to go ahead and put in the other points that are also on the table, but which I don't want to take the time to go through one by one. Okay, so it would look something like this if you were to plot all of the rest of the points. So again, I'm going to kind of just connect these, and we see that our graph is shaped something like this. So to sketch these two graphs, we made tables that included values of t, so input values are angles, that were between 0 and 2 pi. And we already mentioned how, there's angles between those angles, right? The angles that we focused on are basically just the nice ones that are easy to do on the unit circle, but that doesn't mean there's not angles between. Additionally, there are also angles that are less than 0 and bigger than 2 pi, right? You can have angles that are as big as you want that kind of include all these extra rotations around and then kind of landing at maybe one of the nice angles that we're used to. And so the graphs of sine and cosine are not restricted to just being between 0 and 2 pi. So I want to kind of write that down. These graphs, and I'm going to draw a little arrow above because we're also going to have a graph below, so I want to make sure that's clear I'm talking about these graphs, show f of t is equal to sine of t and g of t is equal to cosine of t, specifically for values of t that are between 0 and 2 pi. So what happens if you kind of zoom out and look at values of t to see what the graph looks like, not just between 0 and 2 pi? So what we're going to see is that the shape of the graph is going to repeat itself. So if we look at the graphs for all values of t, so zooming out and not just focusing on between 0 and 2 pi, or sorry, for all values of t, we'll see that their shapes repeat themselves every 2 pi. Okay, so what do I mean by that? Well, here is a picture of the two graphs. So I know there's kind of a lot going on in this picture, but let's focus for a second on the graph that's graphed in red here. So that is our graph, f of t is equal to sine of t. So I'm just going to trace over the part of the graph that we just did together. So from 0 to 2 pi, that is this part of the graph. Right? It looks a little bit different because just the scale of the x and y, or the horizontal and vertical axis, but it's the same shape as what we just saw. So now notice what happens from 2 pi to 4 pi. From 2 pi to 4 pi, the graph does that same exact pattern, right? It goes through all that same shape. And then it's going to actually keep doing the same thing again. And then the same thing to the left of 0. So you can't see all of it, but it would have a shape that looks like this to the left of 0. So oftentimes, when we're sketching the graphs of sine and cosine, we focus on just sketching between 0 and 2 pi because that really captures the entire shape. You're just going to see that same shape repeat itself. And then similarly with cosine, we sketched this part of the graph, right, between 0 and 2 pi. And so that matches up with the shape that we saw up here, more or less. But if you look between 2 pi and 4 pi, you see that it does that same shape again, right? It goes all the way back down, it comes all the way back up. And then similarly here, if the graph wasn't cut off, we would see the same shape again. So it keeps repeating every 2 pi, just like the graph of sine does. And this is something we're going to get a lot more into in our next video, but just to briefly mention, why do these graphs repeat themselves? It basically boils down to the fact of coterminal angles. So if you have an angle that is bigger than 2 pi, like let's say you have the angle 13 pi over 6. 13 pi over 6 is coterminal with pi over 6, right? 13 pi over 6 would be 2 pi plus pi over 6. And so remember that coterminal angles have the same terminal point. And so sine and cosine of 13 pi over 6 is going to be exactly the same as sine and cosine of pi over 6. And so what ends up happening is that all of the outputs that we're getting when we choose t values between 0 and 2 pi, we're just going to keep seeing those outputs come again as we go through these bigger angles that are coterminal with the angles between 0 and 2 pi. So again, I know that I didn't explain that completely thoroughly. We're going to get into that in our next video, so I don't want you to worry about it too much for now. Let me just show you on Desmos kind of even a fuller picture of what these graphs look like. So here is f of t is equal to sine of t. So here we see 0 to 2 pi. But if I keep scrolling, 2 pi to 4 pi, we see that same pattern. 4 pi to 6 pi, 6 pi to 8 pi, and you can just keep scrolling and this thing just keeps going. You can plug in as big of an angle as you want, and it's always going to be land on the unit circle somewhere and give you sine and cosine, and you can plot the points the same as we did for between 0 and 2 pi, and then same thing in the negative direction. And then same thing with cosine, and maybe I'll even zoom out to really emphasize this, right? These graphs just kind of keep repeating and repeating. So here's cosine. One other thing I just want to show you while we're on Desmos. So notice, like over here, I had the horizontal axis labeled in terms of pi. I just want to show you how you can do that. So if I were to go to this wrench symbol, actually you probably can't see that because of how the window is set up. Maybe let me try to move it over. So hopefully you can see now the wrench symbol here. It says graph settings. If you click on that, here it says step. If I were to change this step to 1, what we would see is that the graph is now labeled 1, 2, 3, 4, 5, 6. And notice that, for example, pi is still landing where you would expect it to, right? It's just after 3, and pi over 2 is somewhere around 1.5. So, the graphs still kind of land where they're supposed to, but it's not as nice for really seeing exactly what's going on. And so what you want to do in order to get the things in terms of pi is go to where it says step and just change it to any kind of fraction of pi. So I'm just going to type in pi, lowercase pi, and then I like to do pi over 6, and then that will give us all the kind of divisions that we want to see all of our angles. Okay, couple more things I just want to mention before this video ends. So, we plotted a lot of points to come up with this, right? It took kind of a lot of time to set up this whole table and plot all these points. My goal for you is for you to be familiar enough with the shapes of these graphs that eventually, not today, but eventually you'll be able to sketch the graphs quickly without having to plot all of these points. And so this is something we'll touch more on in our next video, and I actually ask you to do this on your worksheet as well. But one nice thing you can do to help you sketch the graph quickly is focus on just a few key points. So for example, if you just focus on the angles of 0, pi over 2, pi, 3 pi over 2, and 2 pi, those are actually really fast angles to evaluate sine and cosine of, because you don't need to draw a right triangle, right? Those are the ones where it's just pretty easy to look at the unit circle and see what the coordinates are. And so if you can evaluate sine and cosine of 0, pi over 2, pi, 3 pi over 2, and 2 pi, you can get these 5 points plotted. And then all you have to remember is that the graph has kind of a curved shape between them. And really that gets you more or less the graph. And so that's something I would recommend moving forward. There are going to be some times when you want to be accurate with plotting every point, but sometimes you just want to know what the general shape looks like. And so I really recommend just focusing on a few easy points to find the general shape. All right, one more question I just want to ask, just to kind of go back to something we talked about at the beginning of the video. to reinforce this idea of how can we tell which points lie on these graphs. So this question is asking us, does the point 13 pi over 6 comma 1/2 lie on the graph of f of t is equal to sine of t? So how can we check this? Well, remember that any point that lies on a function, the x-coordinate or the horizontal coordinate should be your input, and then the vertical coordinate should be your output. And so if this point does lie on the graph, if we plug 13 pi over 6 into the function, we should get 1/2. So let me write that down. If the point 13 pi over 6 comma 1/2 does lie on f of t is equal to sine of t, then it should be true that f of 13 pi over 6 is equal to 1/2, right? That's really what it's saying when you say a point lies on the graph of a function. If you plug the input in, you get the output. And then what's another way of saying f of 13 pi over 6 equals 1/2? Well, that would be sine of 13 pi over 6 is equal to 1/2. So basically, if we want to check whether this point lies on the graph, we need to verify this. We need to check, does sine of 13 pi over 6 equal 1/2? And so we can check that just by looking on the unit circle. So as we just mentioned a moment ago, 13 pi over 6 is bigger than 2 pi, right? So 13 pi over 6 is going to be equal to 2 pi plus pi over 6. So it's coterminal with pi over 6. So it would be an angle where you go around the circle once and then you come back to pi over 6. So this is our angle of 13 pi over 6. And so what are the coordinates of this point? Well, the x-coordinate is square root of 3 over 2, and the y-coordinate is 1/2. And so it is true, right? Because sine of an angle is equal to the y-coordinate of the terminal point of that angle. And we can see that the y-coordinate, when we're at an angle of 13 pi over 6, is in fact 1/2. And so we can say, yes, it is true. So again, it's just like any function. How do you check whether a point lies on the graph of a function? You kind of just plug that point in. And in this case, that involves evaluating sine of an angle and figuring out whether we get the required y-coordinate or not. All right, so like I said, in our next video, we're going to work more with the sine and cosine graphs. We're going to talk about some different properties of them, their domain and range, other stuff like that. And yeah, I'll see you all in our next video.